presenting two papers. One is UniSim. It's a team of people at Wabi and some academics. They build a compositional scene representation to best model 3D world and then use it for simulation end-to-end learning in robotics. And then there's another more, I would say, almost philosophical presentation by Animesh Garg from Georgia Tech, NVIDIA, and that's about structure in AI. So in a nutshell, what he's trying to solve, or he's trying to answer the question, what is the what kind of tokenization should we use? How should we even, what kind of priors should we use when we look at the world? Like no matter how much data-driven learning we want to do as model designers, we're still using priors, and I think tokenization is a good summary of that. So whatever you choose to tokenize, that's your prior, that's your inductive bias. Okay, if I tokenize words in a text, then my bias is that I'm going to look at this piece of text word by word. I could tokenize paragraphs, I could tokenize letters, I could tokenize spaces, I could tokenize even fractions of letters, but certainly some priors are more useful than others. So Animesh talks about that. I find both of these papers actually related, because when you, in the first one, in the UniSim paper, when you ask yourself, how am I going to model the 3D world? And, particularly if I want to use a transformer type architecture, which I believe they're using, you're going to start asking yourself questions about tokenization, right? And I think Karpati's recent video, I think, made it clear tokenization is not just some sort of data janitoring or one of those things, yeah, somebody, let's have some intern do it. No, this could almost be the crux that solves the model. So because, and this is Animesh's talk, really, it's, okay, what kind of priors should we use? Can we use? Can we learn structure from implicitly? So those are the kinds of questions that this paper is discussing, and I find it really interesting from several perspectives, actually. And excuse me for my indulgence, but I want to even add some art history here. When I look at what modern art did, in particular during the times of Picasso was famous to really take objects, in paintings, whether it's noses, limbs, heads, all that kind of stuff, and totally take it out of context. And in a nutshell, he was asking the question, what is the prior? Does the nose really fit where it's supposed to fit, and is that all there is, or maybe it has another function? Les Demoiselles d'Avignon is, obviously one of the first paintings of Cubism, but then it goes on. I think these questions, they have occupied us throughout modernity, and they're really, really key now, because now we're in the business of, literally replicating the world, turning the world into a digital twin. And when we do that, when we turn the world into a digital twin, we have to ask ourselves what kind of representations we want to use, what kind of priors we want to use. All those things, I think they do matter. This is not even a long podcast. It's April 1st, 2024. This is Krim Dalko. For the day, the fund is down 1.2%. The market is down 70 basis points. For the year, we are down 18%. The market is up 10%. We're underperforming by 28%. So I'm talking about two particular papers. Actually, one is more a presentation with a couple of papers, but doesn't matter. It's two concepts. Let me start with UniSim. So UniSim is a collaboration between a couple of academics and Wabi, and the goal is to build a 3D model of the real world, turn it into a digital twin, and then use it for sim. That's really the fundamental idea. Now, the technical implementation, I think I want to mention just a few things which, bridge the other discussion today, which is the question of structure and priors by Animesh Garg. So the question here is, okay, what do we even use to represent the real world? Using cameras or using LiDAR is already changing the perspective. LiDAR gives you point clouds, and cameras give you some sort of, radiance field. So that's going to change the representation that you get. And actually, let me discuss both because they're really both intertwined. Okay, if you want to use a three-dimensional twin of the real world, let's say you take your own apartment and you're building a three-dimensional twin of your apartment, and you want to teach a robot how to clean that apartment, you're going to come very quickly. You're going to come to questions such as, what priors do I use? What is an object? Okay, what is an object, for example? Is an object defined as something that I bump into? Is an object, what about the bed sheets? I mean, are they they're very, you don't bump into them, right? Or what is my cat? Is my cat an object? Well, it is, but it's going to move away if it gets scared. So versus my chair isn't. So those are all questions that, of course, the 3D sim type people, they don't ask those questions, right? Because they have different problems. Their fundamental problem is how to best represent reality so the robot can learn in sim. That is their fundamental problem. And how best representing reality is a problem of first having a visual representation, but then also a physics representation. And we've spoken about this in the past. There is a case to be made that we can do something like this without any physics priors, just by learning, just by doing. Because if we have enough data samples, and if we can then use Gen AI to maybe augment even more data samples, we could potentially learn the physics just from the data. This is the fundamental idea. The Wabi people basically go down that route. So they have an implicit geometry, which means they learn the geometry of things and the way things relate to each other implicitly from the data. They don't explicitly, they don't use priors. They don't put fundamental priors into the model. I think the reason I discuss this paper is I hope I can bring this home, that we believe that video and sim in general, but particularly video, is most likely going to be the breakthrough that robotics needs. Because in order to have an end-to-end learning machine, we must be able to rely on data itself and the right model, of course, and the right representation. This brings me to the next, this brings me to Animesh Garg's presentation, because I think it's really related. So I don't even want to split those two in this episode. Okay, what is the prior we use? Okay, how do we define the real world? What is an object? And I think one way to attack this problem is by having implicit priors. So have as much data as we can, and then learn from the data and learn structure from the data. That's one way. But Animesh asks a few very interesting questions. The prior, or if you will, the tokenization of the model should be, is partly dependent on the task. In other words, if you want to write a poem, it's probably smart to tokenize the training set by words. If you want to write a marketing summary of something, it's probably not necessary. So now the way large language models work is they have, because of the transformer architecture with self and cross attention, they generalize enough to fit all of these tasks. But what Animesh is saying, that in the robotics world, there could be the case. This is not proven, or this is not a foregone conclusion, but it's possible that we have to tokenize based on tasks. And this brings up some really interesting conversations, that training a model is, on the one hand, we want to have a general model. On the other hand, some of the features of how we train the model, some of the actual model parameters, in particular the tokenization, but other things in the model, they could change with the task. So maybe we should have some hyperparameters that can be tweaked according to tasks. So again, let's say I want to tokenize 3D space for a house cleaning robot in a different way than for a self-driving car, because in a self-driving car scenario, I don't particularly care about the flowers that are on the window on the side road that I pass by and that I capture with my cameras. They're not relevant for my action space. In other words, what matters for me when I represent reality is my action space. If my action space doesn't come into play, then I don't need to represent something. So if my model is supposed to train a car how to drive, the car doesn't need to understand the color of the roses that are on the side road. But if my robot is supposed to paint a painting, then certainly that matters. So in that sense, I think we are embarking on a little bit of a, yeah, it reminds me of cubism. That's why I used in the prelude. How about we, and what Animesh does, by the way, I'm sorry for jumping around. He's using something called NSM, which is neural shape mating. So what they do is they take objects, they break them apart, and then they train a parameterized neural net to fit those things together without priors. And then they learn that while they're doing this, there's some implicit priors. So I think this, to me, this is like cubism applied. This is exactly what Picasso did. He broke things apart. He took, limbs, noses, ears, all that kind of stuff, and started painting people with objects that have no prior explicit meaning or semantic meaning, and that's how cubism came about. And to me, that was rooted in quantum physics and space-time theory and those things, because, and I spoke about this actually yesterday in the episode, if you take space-time theory, seriously, you can say that, look, everything is just a representation on a multidimensional matrix, and depending on which line we go, you could have, your nose could be this way, that way, it could be here or there, it could have different functions. You can throw in there also the multiverse theory and the Harry Potter worlds. We could live in a multiverse where we have 3 noses, or the noses in the back of your head. All that kind of stuff is probably, that's what the multiverse means. So everything that's possible under the laws of physics is actually happening. So in that sense, now back to neural shape mating, the idea here is, again, we break things apart and then we train the model how to fit the shapes. And the reason they do this is because they want to see how those models actually learn how to fit shapes. What are they going to use some implicit priors? And the answer is yes. Animesh talks a lot more about this. Also, he talks about the priors that could be used in not just in object detection, but also in planning. To me, at this point, of course, this has many implications. Fundamentally, it puts us in a position where we modeling the real world, building digital twins, puts us in a position where we have to also answer some really fundamental questions. What is an object? How do I define my interaction with my object? And that's in particular relevant if I'm going to have to use some priors. I'm going to have to use some inductive bias, in particular the tokenization, let's say, in a transformer type architecture. So no matter how much detached I want to be as a machine learning operator, as an AI researcher, I'm not going to get away by excluding myself from the equation. I'm just not going to get away. I'm going to have to at least determine certain priors. And then I think what Animesh is doing with his group is also creating systems experimentally to see how the psychology of the machines actually creates priors. So to summarize, I think these two papers are they're very interesting and philosophically much deeper than I'm giving them credit here. This is obviously just supposed to be a summary and a discussion and also an inspiration. If you have any more ideas, please put this in the put it in the show notes. Excuse me, in the comments, because I feel like this is a lot more important again than I can give it credit to. But at this point, that's I think enough, because I don't want to now be boggled down in a conversation about what is an object and things like that. Let's just leave it at that as a summary, that as an AI architect, I'm going to have to answer some fundamental question about the priors. In particular, when I tokenize a model, like what am I even going to tokenize? What are the fundamental building blocks of training? What is the unit of training that matters for me to have what kind of representation do I apply to have the most optimal outcome? And some hints here. One of the hints is that we could start with the task. And I think where we're going here, so a bit like down Chelsea Finn's alley, is meta learning, having a flexible, parameterized meta model that can adapt to the particular task. So we could imagine a transformer-based model that adapts the tokenization while learning for different tasks. So we could have almost GPT for X, Y, and Z. Now, some of these problems have been solved just by sheer scale, the generalization, but I think what Animesh is going at here is that we don't have the kind of data with robotics. So maybe with robotics, we should be a little bit more careful in how we represent the data that is used for learning. And that could be a route towards more success. And in the UniSim paper, the authors discuss a 3D model of the world, a digital twin that then can be used to run simulations so robots can learn in different scenarios. Thank you.